Use the fresh one. It's not open, right? So,
Hello.
oh, yeah, that's open. And do one.
Okay.
Joined just 1 year back. His research interest is approximation algorithm, algorithmic game theory.
Great, thanks. So you'll hear a lot of researchy talks in this week, some cutting edge work. This is not one of those talks. It's a very gentle introduction to game theory. I realize it's the last talk of the day and I'm standing between you and the final break, so it'll be a sort of an easygoing, sort of example heavy talk. The purpose is to sort of give you a very broad bird's eye view of the field of game theory, which unfortunately is not related to video games, but is a field in economics. And my goal is to more or less excite you about the area rather than to introduce new research topics in this field. So if you are interested in what's the current state of affairs in game theory and more importantly, the intersection of game theory and computer science, then we can talk offline. The talk is going to be more about this classical field of game theory that has received some significant attention from the computer science community in recent years. And the reason for that will become clear as the talk progresses. So broadly, what is game theory? Well, it's a study of interactions of self-interested agents, right? In particular, it's a mathematical study. It's a study that uses mathematical models to understand the models of cooperation and conflict between self-interested entities like human players or organizations run by human players. So there are 4 terms that I'll introduce in the talk, and that are, if you want like 4 technical things that you took away from this these are the first 3, and the 4th one is coming up soon. So the 4 key concepts in game theory, if anyone asks you what is game theory, you can regurgitate these 3 things and a 4th, which I'll tell you soon. But these 3 key components actually constitute the mathematical model that game theory uses to understand strategic interactions. So what are these concepts? The first one is that of a player. So these players model the self-interested agents or the self-interested entities in a game. The second one is that of an action. These are the choices that players make in a game. And these players are self-interested. And their self-interest is quantified by what are called payoffs. So I'll give you many examples, so these things will be fairly clear, but I just want you to, for now, keep 3 terms in mind: players, actions, and payoffs. And they have sort of the natural meaning associated with them as you would imagine. And the key solution concept in game theory is that of an equilibria. And equilibria are model stable or likely outcomes of strategic interactions. They denote settings where no player has an incentive to unilaterally deviate. So that's the mantra. I'll at least repeat it like 10 times in the talk. What's an equilibria? It's a outcome, it's a setting where no player, no self-interested entity has an incentive as quantified by these payoffs to unilaterally deviate, that is, change its own action. So when I say an equilibria, I mean a stable outcome, a likely outcome in this formal sense. Right. So, okay, before moving on to formal definitions and sort of more concrete things, let me give you some illustrative examples. These examples are stylized. The purpose is to sort of hammer in the 4 concepts that I described in the previous slides. The concepts of players, actions, payoffs, and equilibria. So don't get boggled down by the real world details of these applications or these illustrative examples. The purpose is to sort of give you broadly a sense of what a game theoretic model is and what essentially game theory studies. So the first, being in Bangalore, we have to start with traffic network and congestion. There's no way around it. So traffic networks, again, are a sort of a well-studied application in game theory. And traffic networks can be modeled as games, right? They are games in the sense that the players, the users of the networks are the players. The routes that players pick in a traffic network form their actions, right? Every player, every user of the network can pick a route that it can follow, and so those constitute the actions of the players. the payoffs are the delays that the players face. Right, you in the morning, you wake up, you look at Google Maps, you see the current traffic congestion, and as a self-interested player, as a self-interested agent, your decision is the route you pick to go to work. So the players are the different multiple users of the network, their actions are the routes they pick, and the payoff is the delay they face, how much traffic they faced while getting to work. And what's an equilibrium in this setting? An equilibrium is a route choice, is a traffic pattern where no player has an incentive to unilaterally deviate. That is, no user of the network, given the route choices of other network, has an incentive to pick any other route. Right? If it picks any other route, its congestion will only increase. It cannot improve its payoff. So that's a stable outcome of a traffic network. It's a stable traffic pattern, and that's what constitutes an equilibrium in a traffic network. Right, so let me mention that there are advantages of looking at traffic networks through the eyes of game theory, like in this game theoretic framework. And one sort of non-trivial insight that one gets out of this study of traffic networks as games is one can get a quantitative understanding of the so-called braces paradox. So it's a very interesting paradox that emerges in traffic networks, data networks, and what the paradox says is that it is possible, it might happen that if you add an edge in a network, that is, if you introduce a flyover or a new road in a network, then in fact the congestion can worsen for every user of the network. So it's something paradoxical, like I added a new flyover, but it so happens, and this is quantitatively sort of understood through studying equilibria in traffic networks, that such a phenomena can happen. You add more resources to the network, you add more roads, more flyover, and the traffic worsens, not for one person, but for everyone in the network. So that's called braces paradox, and one gets a formal mathematical understanding of such paradoxical phenomena by looking at traffic networks in the framework of game theory. Right. Here's another sort of popular example. This is a major focus area of game theory in recent years has been auctions. Popular examples are these sponsored search auctions that you see on popular search engines like Google. So if you think machine learning makes money, you stand corrected. This is a multi-billion-dollar industry. Like Google, around 60%, I mean this is somewhat of a dated statistic, but around 60%, like multi-billion, a lot of money gets generated by Google through these sponsored search auctions. So if you search a query, on the right hand side you typically see these sponsored search links. Right? These are called, and every time you see them, there's an auction running behind the scenes. These are called sponsored search auctions. And again, auctions are studied typically formally in game theory. And in this context, what's the game? What are the players? Well, the bidder and the auctioneer are the players. And what are their actions? Well, the bids that they place are the actions, and so on and so forth. So again, you can look at auctions in the framework of a game, and you can get some useful insights. Here's a sort of noticeable one. It's a result by Bulow and Kempler that tells you the following. So these are again some like particular examples that I'm telling you to highlight some non-trivial insights that can be obtained by looking at such things in the mathematical framework of games. And this result says that you can obtain as much revenue by running an auction with one additional bidder, okay, in certain settings, but having one more bidder in fact generates as much revenue as you would obtain by running the optimal auction over n people. So say you have a pool of n bidders, and again there's certain technical assumptions that I'm ignoring here, but you have a pool of n bidders, you have an auction with n bidders, and you were to run the optimal auction, right, which can be something very complex. What this result says is in fact you can obtain as much revenue by adding one more bidder to the pool. So the sort of moral is that marketing helps. You can add one more bidder, just one more bidder, and you're guaranteed to get as much revenue as the optimal, get as much revenue with a very simple auction as you would get with the optimal, potentially complex auction with n bidders. So that's so-called the Bulow-Kempler theorem, and again a sort of an insight that you obtain by looking at auctions through the lens of game theory. Right. The final example I'd like to talk about is again that of stable matching, as sort of a very standard problem also introduced in algorithms. And the idea here is that you have two groups of agents, two groups of self-interested entities, say doctors on one hand and hospitals on the other. And doctors have preferences over the, so what are the players? The players are these doctors and hospitals. What are the actions? The actions are the sort of whether to stick to a particular choice of assignment or not. And what these stable matching results tell you is that given these doctors with certain choices over hospitals, given hospitals with certain choices over doctors, so some preference order, you can always find a stable assignment, a stable matching. That is, you can assign doctors to hospitals which is stable in the sense that no doctor or hospital pair has an incentive to switch from the assignment that was, from the matching that was generated. So again, stable matching, something I'm presuming you have, most of you have seen beforehand. And again, non-trivial insight that comes out of looking at these things, formally looking at these things in game theory, is the Stark effect of competition. So there's this recent result by Eshlagi and others that shows that if you add a very slight discrepancy in this setup, that is, you introduce a few more doctors or you introduce a few more hospitals, again, under some sort of assumptions, the quality of the matching can drastically change. Right, so this shows that very little introduction of very little competition can in fact sway the matching from, sway the quality of the matching drastically. Again, sort of an insight which I'm telling you at a sort of an informal level, but the idea is to sort of impress upon you the fact that, yeah, looking at these things from a formal mathematical, from game theoretic perspective does lead you to non-trivial results. So these are the three illustrative examples. I hope in all three you kind of got the concept of what the players are, what their actions are, and what are the payoffs, and what is an equilibrium. Right. Questions so far? Yep.
Does the Stark effect state that the matching will go in a positive direction or in a negative direction?
Okay, formally it's something called like, you could have a doctor optimal or a hospital optimal matching, and it could sway in one of these. Wherever there's sort of deficit, like if you have fewer doctors and hospitals, the matching will just sway to a, like, will be beneficial for the, yeah. So it's something called right, exactly, yeah, something of that sort. Yeah, I'm not expecting you to understand the formal result. I'm just giving you a broad example of something that that comes out of looking at these things from a sort of rigorous mathematical, within a rigorous mathematical framework. Right. Great. So what have I talked about so far? I've talked about the three key components in a game: players, actions, and payoffs. And I also talked about the central solution concept, that of an equilibria. What's an equilibria? It's a setting, it's an outcome where no player can benefit by unilateral deviation. So if others continue to do what they're doing, it's in your best interest, it's in the best interest of the player to stick to what it's doing. So it's again stable in this sense. Right. So before moving on, a natural question is, how is a game represented? Like, how is it given to you? And what we'll look at is the so-called normal form game, which is the most natural way of representing a game. So what normal form means is that I just list out all these components explicitly. I list out all the players, I list out all their actions, and I list out all the possible payoffs that player gets under when different players are playing different possible actions. So that's called a normal form. It's just standard terminology. What I'll not cover in the interest of time are so-called extensive form games. So games of sequential moves like poker or these card games are typically extensive form games. You do something and I do something, the process continues. These are studied under so-called extensive form games. Again, if you're interested in it, you can talk about it offline. But for the purposes of this talk, I'll stick to the most natural and sort of basic representation, which is a natural form game. I just list out the entire components of the game. All these three things I just explicitly list out and then try to understand what are the stable outcomes, what are the equilibria of such a given game. So as I said, they simply include all action profiles, which is all tuples of actions that different players can take, and the corresponding payoffs that each player gets. So let me sort of explain this, delve into normal form games with a very simple example. A simple example of two players. So it's a so-called presentation game. So there are two players in this game, me, I'm the presenter, and you as the audience. And I have two possible actions. What I can do is, I can either put in some effort into this presentation, like spend some time, think of what to say, what to put in, or I can slack off and not put in effort in this. It's evening, it's Monday, take it easy and not put in effort into this presentation. And as the audience, you have two possible actions. It's been a long day, you've been hammered with technical stuff from the morning, so you can not pay attention, just relax, it's nice weather here in Bangalore. Or you can actually pay attention and hope to get something out of this summer school. So two players, you and I, and so my actions kind of index the rows and your actions index the columns. And what these cells mean are the different possible action profiles, right? There are four possible tuples that can happen. I can put in effort, you can pay attention, I can put in effort, you cannot pay, you don't put in effort, you don't put in attention. So four possible action profiles, and what these numbers are these the payoffs that both of us get at all possible action profiles, right? So let's read through this. So what can happen is that I can put in effort and you can pay in attention, and I get a payoff of 2, right? Good karma. I taught you something, you got something out of it, both of us kind of 2-2, right? What could also happen is that you can pay attention, but I can slack off. Okay, not good for both of us. It's bad PR for me, so I get -7, and you wasted an hour. You could have walked around ISC, looked at some beautiful trees and such, wasted an hour, -8 payoff for you, right? So on and so forth. So these are numbers, and this kind of represents a game. Right, and that's a normal form representation of a 2-player game. Right, so again, what are the players? Me, you, both of us have 2 actions, put in effort, don't put in effort, pay attention, don't pay attention, 4 possible action profiles, 4 possible tuples of actions, and the payoffs are as listed in yellow and orange. Great, so let's see what are the stable or likely outcomes of this game. So one stable outcome, which I hope is what's happening right now, is that I'm putting in effort and you're paying attention. So hopefully we are at this cell right now. So why is this a stable outcome? It's a stable outcome because neither of us have an incentive to unilaterally deviate. Say you're paying attention and I stop putting in effort, then my payoff drops from 2 to -7. So if you are paying attention, it's in my best interest to continue putting in effort. So good for me. I mean, if I move from here to here, my payoff drops. Okay, so it's not unilaterally beneficial for me to move away from this state. Also, it's a stable outcome for you, because if we are in this state and you were paying attention and then suddenly you stop paying attention, you're getting something out of this talk, hopefully. But again, if you stop paying attention, then nada, you're not getting anything out of it. So not a benefiting unilateral deviation for you. So by that I mean, if I continue to put in effort, it's in your best interest to stick to paying attention and not unilaterally deviate. So in that sense, this cell, this action profile is a stable and likely outcome. In that sense, this denotes an equilibrium of this game. Note that this is not the only equilibria. Can you point me to another equilibrium of this game? 0-0. Yeah, the wonderful, both of us just slack off. Right. So good. That's another equilibrium. It's not beneficial for me to deviate, start putting in effort. I mean, I put in effort, everyone is asleep, no point. Again, not beneficial for you. I'm not putting in effort. Like if I'm continuing to not put in effort, you suddenly start paying attention, you suddenly wake up. Again, you're not going to get anything out of it. Better for you to sleep. Right. 2 equilibria of this game. So, formally, just to sort of reiterate, this EA, this action profile, where I'm putting in effort and you are paying attention, neither of us has an incentive to unilaterally deviate, and this is also another such action profile where neither of us have an incentive to unilaterally deviate. Great. So what you have seen through this example are what so-called pure Nash equilibria. Right. These are two action profiles where neither of us have an incentive to unilaterally deviate. When we pass through these equilibria in the sense that I've said at least 10 times by now, Nash is the namesake of the person who proved the celebrated existence result, John Nash, and I'll get to John Nash soon. Pure here quantifies the fact that this is a deterministic equilibria. Both of us have a single action profile which we can stick to and sort of not gain by unilateral deviation. So pure just means that both of us ended up having an action profile where there was no benefiting deviation. There was no randomization. It was a deterministic choice. I put in effort, you pay attention, deterministic choice. The other case, I don't put in effort and you don't pay attention. Again, both of us had a deterministic choice. Great. So it just so happened in the case that there were such cells, there were such action profiles with no benefiting deviation. But it's not hard to come up with examples where there are no such cells, right? You can fill in numbers where there's always a benefiting deviation for either you or me. So let me kind of, again, impress upon this observation through another example. This popular game of rock, paper, scissors. So I hope people are familiar. This is sort of a simultaneous move game where both of us pick a gesture and there's certain sort of rules. If I play rock, you play paper, I win, so on and so on. Or no, the other way around. Right. So there's certain rules, you follow them and we'll see what these rules are. But it's, my point is it's again a two-player game. It's a two-player game where both self-interested players, two players, simultaneously select an action, one of rock, paper and scissors, and they want to maximize their own payoff. They want to win. Great. So how do we represent this game in normal form? How do we write it out in the language of game theory? Well, here it is. Two players, the actions of the first player index the rows of these matrices. So the first player has three possible actions, row, rock, paper and scissors. The second player has three possible actions, rock, paper and scissors, and that indices the columns of these two matrices. And all possible outcomes and corresponding payoffs are listed here. So say the first player plays rock and the second player plays paper, then the first player loses, gets a payoff of 1, and the second player wins and gets a payoff, so the first player gets a payoff of -1, second player wins, gets a payoff of 1, so on and so forth, right? So if the second player were to play scissors and the first player were to play rock, the first player would win, the first player would lose, get -1, second player would win, get payoff of 1. I'm writing down the rules of the game in this form. Hope that's clear. Right. And the observation I said before that there is no cell, there's no action profile that constitutes a Nash equilibria holds in this setting. Right. If, for example, say the second player always plays paper, right? Goes in deterministically says, come what may, I'll play paper, then the second player can always play scissors and win and defeat the first player. So there's no stable outcome where both players stick to one possible action, and it's natural. In such a game, the idea is to randomize. Right. So here's one notation that I'll use going forward. What I'll do is I'll use U to denote the utility, the payoff of the two players. The subscript here denotes which player. And the index here is the different action profile. So what this means is that if the first player plays rock and the second player plays paper, or if the action of the first player is R and the action of the second player is paper, the utility of the first player is -1. This denotes this cell right here, right? Rock, paper, -1, and the utility of the second player, the subscript here denotes the second player, utility of the second player is 1. So all I'm doing is notationally writing this entries of this cell out. So what would be like U1 of R comma R? And what would be U2 of R comma R? Great. So at least we are in that attention effort cell. Yes. Great observation. No. Get to it in 1 minute. Yeah. So for this particular game, it just happens to be the case, but I could have defined it any which way. This wasn't the case here, right? So not necessarily. For this game, it just happens. Why is it happening? Because it's a strict competition. Whenever you lose, I win. Whenever I win, you lose. So these are so-called zero-sum games, and I'll get to it in just a minute. A very important class of games, but yeah, for not true in general, here's one example. For this particular game, because it was sort of a competitive game, like whenever I'll win only if you lose and vice versa, this happens. Yeah. Yeah. So this just denotes the actions of the two. So the first index is always, the first argument is always the action of the first player. The second argument of this function is the action of the second player. So this color coding should help you. So R comma P means the first player is playing R, second guy is playing P. So that's why in this one corresponds to this one. Yes? Okay. As I said, there's no deterministic stable outcome. There's no action profile. There's no fixed set of actions that both players can take and that will continue to be in equilibrium. That is, there's no cell where neither of the two players has an incentive to unilaterally deviate. It's a simple exercise. You can just go through it and verify that for yourself. So we must consider cases where players randomize, and it's natural. Like if you have ever played such a game, it is in your best interest to randomly pick one of the gestures. So let's do that. And as was pointed out, it's important to note that this is what's called what's called a zero-sum game. These are a very well-studied class of games, and they model strict competition. They model settings where whatever the first player loses is exactly equal to what the second player wins, and vice versa. So what's a zero-sum game? It's a game where the sum of these two entries is always 0. So it's not necessarily -1 and 1. It could be -8 and +8 or -7 +7. But if you have a game where every action profile, every cell, when you sum the entries, you get 0, that's a zero-sum game, and it models strict competition. Very well studied class of game, and it should be quite natural to you why that is. It's modeling competition, strict competition. Right. So what is a stable outcome of such a game? So in order to do that, let's look at a probability distribution, right? Let's look at a distribution where the players uniformly pick an action. That is, the players pick one of their 3 possible actions, each with equal probability. So let's look at this probability distribution, 1/3, 1/3, 1/3 over rock, paper, and scissors, right? So in particular, let's look at the expected utility, the expected payoff of the first player if the second player follows this distribution. That is, if the second player picks an action based on this distribution. That is, the second player plays rock with probability 1/3, paper with probability 1/3, and scissors with probability 1/3. So what's the expected utility of the first player under all the 3 actions when the second player is picking one of its actions based on this probability distribution? My claim is that doesn't matter what the first player does, its expected utility is always 0. So again, a notational introduction. By this I mean the expected utility of the first player when the first player is playing rock and the second player is picking an action based on this distribution sigma. Right, second player is picking an action randomly, first player is picking rock. What's the expected utility of the first player? My observation is that this is 0. Why is that? Let's just work through it. So with 1/3, so the first player is playing this row. It's first player is playing rock. With 1/3 probability it gets 0. With 1/3 probability it gets -1. With 1/3 probability the first player gets 1. Boom, 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 0. Right. Again, it's sort of, you can just simply eyeball the example and note that doesn't matter what the first player plays. It doesn't matter if the first player plays rock, paper, or scissors, the expected utility continues to be 0. So if the second player randomly picks one of its actions, one of rock, paper, or scissors, this is what the first player is going to get in expectation, 0. Right. So this means that even if the first player were to follow this distribution by linearity of expectation, the expected utility of the first player continues to be 0. So what does this notation mean? This means the payoff, the utility of the first player when the first player is following distribution sigma and the second player is also following probability distribution sigma. Great. I know it's pedantic, but it's late in the day, so let's be generous. Right, so expected utility of the first player when both of them pick an action based on this uniform probability distribution is 0. Again, you can just work through the example. It's almost, it's a sort of a symmetric case. So you can also work through these numbers and see that this will also happen for the second player. So if the first player were to follow distribution sigma, that is the first player were to pick one of its 3 actions based on this uniform probability distribution, doesn't matter what the second player does, the utility of the second player, the expected utility of the second player is 0, i.e. in expectation, when both players are following distribution sigma, the utility of the second player is also 0. So, okay, here's a quick question. I didn't have to do this calculation. This implies this. Can you tell me why? It's a zero-sum game. Irrespective of what the distributions are, the sum of these two expected values is always 0. Since this is 0, the sum is 0, this is also 0, right? It's a zero-sum game, right? Not only for every action profile is linearity of expectation, this would continue to hold irrespective of the distributions that the two players are playing. But yeah, so under this distributions, both players are getting 0. My claim is that at this distribution, when both players are playing the uniform distribution, neither of the two players has an incentive to unilaterally deviate, right? This, in particular, constitutes a Nash equilibrium of the game. So if the second player continues to follow distribution sigma, doesn't matter what action the first player picks, it's also going to get 0. The first player cannot benefit. If the second player is playing sigma, the first player cannot benefit by switching to any other action. It's getting 0 irrespective of what it's doing. And also, if the first player continues to follow distribution sigma, the second player cannot benefit by unilaterally deviating from sigma, because it doesn't matter what the second player does, it's also going to get 0. So no benefiting unilateral deviation, i.e. this pair of uniform probability distributions constitutes a stable outcome. It constitutes what's called a Nash equilibrium. I know I haven't formally defined Nash equilibrium, but I hope sort of the broad strokes are clear. What I mean by a Nash equilibrium, what I mean by a stable outcome in game theory.
So R, P and S may not be the
No.
only ways we play, right? So we have to judge it according to each and every player. I think there should be he may probably choose different probabilities.
Right.
So we have to compare sigma with all the other cases as well. Then only can we say that it's a Nash equilibrium.
It's so, okay, yeah, note that it's not, what you're saying is I might not be best responding to the other guy, but it's an important point, and let me kind of speak to it. What this is saying is sort of stable in the sense that given, like, it's stable, it's an equilibrium, like a body is an equilibrium. Given that the other player is doing this, you have no incentive to deviate and vice versa. You can show that, and there could be multiple Nash equilibria, but this is one of them. Right, but note that the cycle has to end somewhere. Like you are playing some distribution, I play a distribution that's a best response against it. I play something that maximizes my payoff against your distribution. But then you will do the same too. Right, and the cycle continues. Where will this converge? It will converge to this point. Here, you are doing this, I am best responding to you, and at the same time, if I am doing this, you are best responding to me. So that's an equilibrium in this sense. We both are at the same time simultaneously best responding to each other, hence an equilibrium. Classically, it was called saddle point, like before John Nash's theorem, but yeah, it's in that sense, yeah, it's stable. You can think about it that way, but mathematically, these are different beasts. Saddle point of functions and versus this, yeah. It's sort of more related to what's called a fixed point. I'll get to it later. But yeah, it's good, like rough intuition to keep in mind. Can you speak a bit louder, please? No, not necessarily. I mean, it's just a simple example. It's a simple illustrative example I gave. It's completely not true. I mean, make this 0, 0. Or sorry, yeah. I mean, you can change the numbers to force the equilibrium in one direction. It's simple examples. We talk about it offline. It's just this particular example. Instead of -1, 1, if you change these numbers, you'll see that the distribution will change. But yeah, I encourage you to work through this. It's certainly not the case. That would be too much to ask for. Good? All right. So, finally, here's the formal step towards defining a Nash equilibrium. What's a Nash equilibrium? It denotes a probability distribution where neither of the players can benefit by unilateral deviation. I think you'll dream of this. I've said it so many times that come in your dreams or nightmare. Right. So let me kind of pass through this in a more formal way, just because I'll need it to define certain things. But here's the notation. I'll use this set to denote the set of players. So in the presentation game we saw, there were 2 players, you and me. So n was 2. So 2-player game. The players P's action set is this AP. So again, in the presentation game A1, the action set for me was put in effort, don't put in effort. And the action set for the second player, U, was pay attention and don't pay attention. Right. So that's that. The Cartesian product of these action sets is what I call action profiles. So the 4 cells in the presentation game I showed you are the action profiles. And what's the utility function? It's a function that maps an action profile to a number. So that's it. That's the specification of a normal form game. And I already have shown you 2 examples of it. Again, in the rock, paper, scissors, 2 players. The one whose actions were indexing the rows, indexing the columns. The action sets were rock, paper, and scissors. And the utility functions were as I had described. Right? Good. And here's the formal definition of a Nash equilibria. Looks a bit dense, but let's pass through it together. Hopefully it will be understandable. A collection of probability distributions is called a Nash equilibria. It's defined to be a Nash equilibrium if this happens. What is this? This says that this denotes the expected utility of player P if the player follows its distribution sigma P and the others continue to follow their own distribution. So the sort of clunky but standard notation in game theory, sigma subscript minus P denotes the distribution of all other players besides P. So this says that let the other players keep doing what they are doing. It's in the best interest of the player to follow sigma P. That is, the player P cannot benefit by switching to any action in its action set. For any player, there's no unilateral benefiting deviation. That's all that this sort of is saying mathematically, right? So we saw 2 examples, and it just so happened that both of them had Nash equilibria. Both of them, like in the first game, there was in fact a point mass where 2 point masses where the players had no incentive to unilaterally deviate. In the second one, there was this uniform distribution that no one had an incentive to unilaterally deviate. So the question is, did we get lucky or is this a recurring phenomenon? And as it so happens that this is true in quite a bit of generality. So the fundamental results of game theory that show that any finite game always admits a Nash equilibria. It's a sweepingly general result. It's quite impressive, and you should be sort of taken aback by it. It doesn't matter how many players, as long as you give me a finite number of players, as long as you give me a finite number of actions for each player, does not matter what the utilities are, there always will be an equilibrium. There always will be a stable outcome in the sense that I have defined before. And these 2 results were proved by these 2 gentlemen here. These are the 2 rock stars of game theory. The gentleman to your left with the big head is John von Neumann, who proved this result for zero-sum game, two-player zero-sum game. And the gentleman to your right with the big head again is John Nash, who proved it for general finite games, not just two-player, but any finite games. So what I'd like to do quickly towards the end of the talk is present this result in some detail, and I'll leave the general result for you. So it's somewhat involved. Right. So von Neumann's result is that every two-player zero-sum game admits a Nash equilibrium. So what's a zero-sum game? This is an example of a zero-sum game, but in general, this just means that the utility of the first player, when the first player plays action 1, second player plays action 2 for any choice of actions is 0. It's this sum is always 0. At any action profile, the sum of the utilities is 0, equivalent to saying that the utilities are negations of each other. That's the definition of a zero-sum game. Rock, paper, scissors was an example of a zero-sum game. Right. So in this context, a very useful quantity to study is what's called the maxi-min value. So this is a definition. Give me a game and I can define a quantity. I'm free to do so. And this is what I define. It turns out to be a useful quantity, but let's see why. So note that an equilibrium is a simultaneous move concept, right? When you, at an equilibrium, you are free to look at the other player's distribution and react. But when I'm defining a maximum value, I'm looking at a more pessimistic, I'm going with a more pessimistic outcome, and this is the quantity I look at. This is the largest value that player 1 can guarantee for itself if it's forced to move first. So let's parse through this. The order of optimization is important here. So what this says, we always parse these things left to right. So what this quantity says is, let the first player pick a distribution, sigma 1, and it's trying to maximize its utility. So it picks a distribution that maximizes its utility, but then the second player gets to go second and pick a distribution that hurts the first player the most. It's a zero-sum game, so it's in sort of the best interest of the second player to pick a distribution that minimizes this. But the first player kind of says, okay, what's the distribution that I can pick, such that doesn't matter what the second player does, I'm at least guaranteed this much payoff. That quantity is called the maxi-min value, right? And so again, the order of optimization is important. I'm moving from the left to the right. I pick a distribution, the first player picks a distribution, then the second player picks sigma 2 with respect to sigma 1 so as to minimize this. Great, that's the maxi-min value. Analogously, I can define, okay, let me introduce sigma 1 star, which is the maximizer of this expression. So I've done nothing, I'm just saying, let sigma 1 star be the distribution that achieves this maxi-min value, right? First player goes first, second player then goes looking at sigma 1, and this is the order of optimization, left to right. That's the maxi-min value. Sigma 1 star is the distribution that achieves the maxi-min value. So it's a distribution or the action set of the first player. I can also define the so-called minimax value, wherein the second player now has to go first. Again, the order of optimization is left to right. So the second player picks a distribution sigma 2 so as to minimize this quantity, but then the first player can go and sort of play the best against sigma 2. And this is called the minimax value, right? So one of these quantities is like, it's simpler to see that one of these quantities is bigger than the other. Can you tell me which one? Like, what's the likely relation between these two values? This is greater than 2. Okay. Any other? In this, not too many choices. You can say the other one. So note that, yeah, the order of optimization is here. The first player has to go first, has to commit to sigma 1. When it commits to sigma 1, the second player moves in and says, you are playing sigma 1, let me play sigma 2 so as to minimize this. But the first player plays sigma 1 such that it gets as large a value as possible. Here it's the other way around. Okay, what happens is that, and this is von Neumann's result, that these two values are equal. Does not matter in which order the two players pick their distribution, the minimax value turns out to be equal to the maximum value. If you know LP duality, this is not hard to prove, but in and of itself, it's an interesting result. In the interest of time, I will not prove this theorem, but what I will do is use it to show the existence of Nash equilibria in two-player zero-sum games. Right. Note that all of it is defined with respect to U1, and it's just the order in which these two distributions are picked. In equilibria, this is not the case. In equilibria, both players, it's a simultaneous move game, so both players pick their distributions simultaneously. Right. So what this says mathematically is I can just repeat this definition. Maximin is equal to minimax, or I can use sigma 1 star to write that min of sigma 2 here is equal to this minimax value, and again on the right hand side I can replace this by just notationally use what sigma 2 star is to get this equality. All I've done is restated the minimax theorem, the fact that these two values are the same, using the notation of sigma 1 star and sigma 2 star. Right. So quickly what I'll do is I'll show this, that if you have this theorem, then you can show the existence of Nash equilibria in zero-sum games, any two-player zero-sum games, and the proof is slick. It will fit into this much of space. So if you're sleeping, this is a good time to wake up, or not. So here's what we have. This inequality follows arbitrarily. Let's say the first player plays distribution sigma 1 star, the one that achieves the maximum value. The second player plays sigma 2 star, the distribution that achieves the minimax value. And I have this inequality. This is simply because this is one particular distribution, and here I'm minimizing over all possible distributions of the second player. Right? Sigma 2 star is one particular choice here, and I'm looking at all possible distributions. So naturally I have this inequality. Right, but note that this is exactly the left-hand side of my minimax theorem. So this is equal to the maximum of this thing. I just use this equality here. But what does this say? This says that if the second player is following distribution sigma 2 star, the best that the first player can do is in fact sigma 1 star. Any other distribution will not fetch the first player a utility better than this if the second player is playing distribution sigma 2 star. I.e., doesn't matter what the action of the second player is, I have this equality. This is exact. You look at the extreme left hand side and the extreme right hand side, you get the definition of a Nash equilibrium. It's almost slick. So think about it offline, but that's it. That's the proof. If you have minimax theorem, this says that if the two players are playing these distributions, the first player cannot benefit by deviating to any action in its action set. The second player continues to play sigma 2 star. In a zero-sum game, what happens is that U2 is equal to minus U1. So sigma 1 star, sigma 2 star analogously are the minimax and the maximum value for the second player, and you have the exact chain of inequalities for the second player as well. So again, if you just rework through the numbers using the fact that U2 is equal to minus U1, you get a similar inequality for U2, which is equal to minus U1, and you get that the second player can also not benefit by unilateral deviation. So that's it. That shows that we have a Nash equilibrium in the game. In particular, the minimax and the maximum distributions constitute a Nash equilibrium in a zero-sum game. Right, again, I didn't talk about the proof of this theorem. It follows from linear programming duality. Sort of interesting result in its own right. It's a very useful result for lots and lots of applications. Right, two rock stars of game theory, and I just kind of talked about two-player zero-sum games. What John Nash showed was this holds in complete generality. Nash's result, again, definition of Nash equilibria, I hope you remember this. So this is the celebrated Nash's existence theorem, which shows that in every finite game with a finite number of players, a finite number of actions for such players, there will be a Nash equilibrium. Again, a sweeping result which you should find impressive. It's non-trivial in a very deep sense. And the proof of this follows from what's called Brouwer's fixed point theorem. Very heavy hammer. It's a completely non-constructive result. This is sort of a solid piece of math right here. Beautiful math, but this is deep stuff. Right, so I talked about two classical foundational results in game theory. So if someone asks you down the line, what did you hear in game theory? This is it. You heard about Nash's existence theorem, and that should be a takeaway from the talk. Let me quickly wrap up since I'm almost running out of time. So this kind of concludes what I wanted to talk about classical game theory. There's lots and lots of things I didn't cover. It was tip of the iceberg. This is sort of the foundational result. This is 1950s stuff. So you can understand last 60 years there's been extensive lot of more work in this area. So sort of the beginnings of game theory, if you will. So what I do want to talk about in the last 5 minutes is this very active and impactful area of research at the intersection of game theory and computer science. It's an area called algorithmic game theory. So game theory talks about existence results. When you look at these problems, when you look at classical economics from a computational perspective, what you get is algorithmic game theory. And a central thread of research in algorithmic game theory, and some work that's kind of being done at ISC right now, is about computational aspects of Nash equilibria. I told you that every game has a Nash equilibria. Not just zero sum, but even not just two-player games, but any arbitrary finite game has a Nash equilibria. But how can you find it? Right? Can you find it efficiently? Right? You're using this equilibria as a model of outcome. You're using it to predict the behavior of a strategic interaction. To do this, you have to compute this efficiently. So that's sort of a central theme of algorithmic game theory, looking at algorithms and hardness results for finding Nash equilibria. Let's start with one positive result. It so happens that in zero-sum, two-player zero-sum games where you have two players and the sum of utilities is always zero, you can in fact find Nash equilibria efficiently. You can do this because you can find minimax strategies efficiently via linear programming. So I hope everyone knows that linear programs can be solved in polytime. Why is that? What's the name of an algorithm that does it? Gaussian elimination, linear programs, not system of linear equations. LP, I give you a linear program, you can solve it in polytime. Linear programs, not NP. Okay, interior point methods or ellipsoid algorithms. Yeah, so that's a talk for another day and another hour. But linear programs can be solved efficiently. You don't have to take my word on it. Like books and courses are offered on the subject. But because you can do that and because minimax strategies can be computed via LPs for zero-sum games, you can find Nash equilibria efficiently. But the train of good news stops here. The history of algorithmic game theory has been a history of impressive bad news. It so happens that without a modulo few exceptions, this is fairly hard. It's computationally hard to find Nash equilibria in general two-player games, and let's not even talk about multiplayer games. So this is sort of a fairly computationally hard problem, and turns out understanding approximation results for it, understanding cases where this complexity can be circumvented, understanding structural results that will let us bypass such, like identify specific cases where equilibrium computation continues to be efficient, continues to be in polytime, is a very active and interesting area of work. And if you are interested in any such questions, please talk to me offline. I'll be happy to talk about it at depth. Right, so let me conclude quickly. I did not cover a number of things, as I said. It's 1 hour and it's a topic that worthy of a full course in and of itself. What I didn't talk about, as I mentioned, is extensive form games. So if games like poker or chess, or like these are studied in this umbrella of extensive form games. Another important thing I didn't talk about are these no regret dynamics. That's the connection between game theory and machine learning. So if you hear learning theory, the bridge is through these so-called no regret dynamics. And there are other notions of equilibria too, like not just Nash. You can look at more general classes of equilibria, other types of equilibria, for example, correlated equilibria, coarse correlated equilibria, so on and so forth. Again, I encourage you to take a look at, if you're interested, take a look at any of these classical books. And let me stop here. Thank you. All right. Questions? Or it's too late in the day, huh? All right. Thank you.
Small token of appreciation.
All right. Thanks.